Thanks. So this is a joint work with my advisor, Andreas Krause at ETH. So this work is mainly math in nature, but I want to start off with a couple of motivating examples. So our first example comes from the field of combinatorial auction. So suppose you have some set of objects you want to get rid of and sell them off to a bunch of people, and each of your bidders has a certain valuation function. That is, for every subset of these objects, they value it some certain amount, and it's the value of the individual objects may depend on the other objects in some interesting way. And we're not interested in the problem of allocation that auctioneer would also be interested in, but just simply how do you learn these valuation functions? So you show bidders various subsets of these objects. So there's 10 objects here. So here's one subset. This bidder evaluates it some amount, and so on. And the question is, how many bids do we need, and what model do we need in order to learn this valuation function? So this valuation function is an example of our general object of study, which is a set function, which is any mapping from a power set to, say, the real numbers. So our second example may seem at first to be quite different because there's no set function here. So suppose we want to track changes in some very large graph. And we'd like to do this without having to store the entire graph. So we just want to see what's different between this month and last month. And we would like to do this without having to store last month's graph, look at this month's graph, and then compare the two. We'd like to just store some relatively small set of measurements, and then just use those measurements to detect what's changed. And the assumption here is that the graph hasn't changed too much. So here only a few edges have appeared or disappeared. And the assumption is that the number of measurements that we're going to need is proportional to the number of changes in the graph. But so what are these measurements that we propose to make? Simply just random graph cuts. So you just take a random partition of the graph, and then you look at the cut across that partition. So equivalently, color each vertex in the graph red or blue with probably 1/2, and then just look at the edges that connect a red vertex with a blue vertex and count them up. And so then you do this with the same random partition at your different time steps, and then the count will change from one time step to the next, and that's one measurement that you've made of the graph. And then you're going to need to do this several times. So you're making these sort of random measurements of this graph, and if you have enough measurements, you can actually reconstruct what has changed in the graph, if that's what you're really interested in. So again, like, you're not really interested in maybe the entire social network of people around you. Maybe you just want to see like who's broken up with whom recently or something, or just where the edges have changed. And so what does this have to do with set functions? So you can think of these random graph cuts as samples of a set function, which is the symmetric graph cut function. So if you, this function maps a subset of vertices to a real number simply by looking at the sum of weights between one set and then the complementary set. And so without going into the details, it's pretty straightforward to show that there's a one-to-one correspondence between graphs, or weighted undirected graphs, and these sorts of cut functions. So if you can learn the cut function, you can learn the graph. And also, if you can learn changes in the value of the cut function, then you can learn what's changed in the graph, if that's all you're interested in. Okay? And so this is also strongly related to a problem that's been studied in theoretical computer science. Is how can we learn a graph from additive measurements of the graph? And I think that's been motivated in computer science from bioinformatics. But our work is not just theoretical, but we also actually try out the algorithm, or implement our algorithm and try it out on some real-world data. And so the general problem is just simply, we've got some sort of set function, and we want to learn it. And so a side note, set functions, of course, are also known as pseudo-Boolean functions, because the power set is equivalent to the Boolean cube. So as a special subcase, this would include, say, just learning Boolean functions. So there's a lot in the literature under the name Boolean and pseudo-Boolean. But so we're just studying this. Our approach, this isn't a new problem, but our approach is to, you'll see, is somewhat new. So we've got presumably small measurement collections. We're evaluating the set function on some small collection of sets, and we know what that collection is, and then we see those function values, and then how are we going to infer what this function is? And so, of course, we need some sort of modeling, some sort of regularity. And so the way we approach this is as a problem in sparse recovery. And so we just think of this as we're making linear measurements of a system, of an object, and if we can assemble that object in some basis where it's sparse in that basis, then perhaps we can use techniques from sparse recovery. And so the equivalent, there's a very strong connection here between a very similar problem in compressed sensing, where you might be trying to reconstruct a function which is sparse in the Fourier domain. And we'll see that this, in fact, there is a set function equivalent to the Fourier transform. So this is an application that people are actually interested in, is how to detect a very high frequency radar pulse where you actually don't want to, it's so high frequency you don't actually want to build a sampler that samples at the Nyquist rate. Traditional sampling theory would tell you that if you have a band-limited signal and it's high frequency, you have to sample, if you're sampling regularly, you have to sample at the Nyquist rate, otherwise you'll never be able to reconstruct it with any accuracy. However, if you also know that the signal is sparse in the Fourier domain, you can actually get away with random sampling, where the average rate of random sampling is on average below the Nyquist rate. But then you're going to need to use results from sparse recovery in order to reconstruct it. You can't just linearly interpolate. But so this is related to one of the first papers in compressed sensing by Candice Romberg-Tau, where they specifically studied the Fourier ensemble and how can you reconstruct something which is sparse in one domain given random measurements from the other domain. So again, so our work, we're just going to, for this presentation, I'm just going to focus on L1 minimization. And of course, there are many extensions to this, like reweighted L1 and noise-aware variance. And our paper actually includes noise-aware variance. And of course, you can also use greedy methods. And if you prefer, they would work just as well here. The main insight is that you can approach this problem as one in sparse recovery. So the basic setup here is you've got some vector and some high dimensional space and some set of, so the high dimensional space is P. I say M is the number of measurements. You want the number of measurements to be much less than P, and you assume that it's sparse in, the original vector is sparse with some sparsity K. And so the question is, when will this L1 minimization program ever recover the original vector exactly? So this is a convex optimization program, so it can be run in polynomial time, but you need some conditions. It won't work for arbitrary matrices V. So one sufficient condition, which is fairly strong but is still quite useful, is the restricted isometry property. So this is standard if you're familiar with compressed sensing stuff, so I won't get into the details. I mean, it's kind of a technical definition. But the key thing here is that our random measurements of set functions will satisfy the restricted isometry property if we use recent results from random matrix theory. So, I mean, again, Candace, Romberg, and Tao originally studied the Fourier ensemble, but more recently, some of those results have been superseded by Vershinin and Rauhut. They've improved the log factors here. But essentially, if you randomly sample the DFT, then RIP holds, and then L1, this L1 minimization program will exactly recover a sparse vector. And of course, RIP is also a very useful condition for a lot of greedy methods, like OMP. A lot of proofs of OMP involve a RIP condition as well. So the main questions of our work is, so this is all well known in the sparse recovery community, but can we extend this idea to set functions? And then furthermore, so that's just a merely theoretical consideration, but then can we also develop some practical recovery algorithms, because we have potentially exponentially many parameters here. And we can't even, it's hard to even represent an arbitrary set function in memory. So the key tool here is what I call the set function Fourier transform, because I think of it just as the Fourier transform on the Boolean cube. And a lot of your favorite properties of your discrete Fourier transform hold here, like Parsifals, and you can define convolutions, you have a convolution theorem. So it's, as you would expect, an orthonormal basis, and so you have a reconstruction formula. But an interesting thing about this is that you can't, if for an arbitrary set function, so if I have Oracle access to a set function f, but I know nothing about it, I can't even, in any reasonable sense, compute a single one of those coefficients, because it has exponentially many terms. So even just to compute one of these coefficients, we're going to have to make some assumptions. But you can compute lots of functions that you know in closed form. You can compute their Fourier transform. And so we represent our set functions as superpositions of these Fourier modes. So down there I've got psi b. So the Fourier modes are indexed by a set, and the size of that set is what we call the order. So the 0th order mode is just the constant, a constant. And the Fourier modes oscillate on that set. So when you add or subtract, or when you add or remove an element from that set, the sign of it changes. So you can think of the high order things as corresponding to like a high frequency Fourier mode, and the low order ones corresponding to a low frequency thing. And okay, so in order to apply results from random matrix theory, we're going to choose, we're going to study when the collection of measurements has been made by choosing each measurement set independently and uniformly from the power set. And so, for instance, that means corresponds to random partitions. So we just need to introduce some vector matrix notation. It's just a change of notation where we're just putting all our measurements in a single vector. And just to put this notation, so it's similar to the language of sparse recovery, we put all our Fourier coefficients, and right now there's still exponentially many of them, and we write it as a vector matrix equation. And then, so simple theorem from recent results from random matrix theory is that RAP will hold, and so then of course if you could solve this L1 minimization problem, you would be able to reconstruct sparse Fourier sparse set functions. And then you can extend it to noisy variations. So of course, we need to somehow cut down the size of this, this set, this collection that we're searching over. And we can't handle arbitrary sparse set functions, but there are some special cases that we do consider in our work. So first is simply if you know that the function is low order. So it can be represented as a sum of a few things of subfunctions which depend on only a few elements at a time. So for instance, graph cuts are order 2, so we can ignore all the higher order coefficients other than things that are order 2 or below. Likewise, a lot of functions are symmetric by construction. That is, they're equal on both a single set and then the complementary set. So a lot of set functions in machine learning, like mutual information and energy functions for clustering, are symmetric by construction. And the implication of that is simply that all the odd modes are 0. And then other simple things, if you know that the function is positive, then that implies that the 0th order coefficient dominates all the other ones in magnitude. And likewise, if you know that the function is increasing, then you know that the first order coefficients must dominate all the higher order coefficients. Specifically, the higher order coefficients which contain an element must be dominated by that first order coefficient. So that tells you something about where the support can, what sort of structures you can have in the support, and the fact that the coefficients must decrease or cannot increase. And of course, Andreas does a lot of work in submodularity, and this is very natural for valuation functions, where when you add an element to a set, the incremental value of adding that element is smaller for a larger set because it has less of an impact. And equivalently, that means that second order differences are negative, which means that the second order coefficients have to dominate in magnitude all the higher order coefficients. So in summary, we've got some restrictions on the Fourier support so that we don't need to explore all exponentially many subsets. And then we've got some nice linear constraints on coefficients so that we can implement those as part of our convex recovery program. So we're going to cut down the collection to some collection. We're going to cut down where we look for our Fourier support to some collection P, which will depend on the problem. Like for our symmetric graph cut functions, it's just the empty set and the size of order 2. And so now we introduce that into our matrix notation. So now this is a much more reasonable matrix equation, something we could actually hold in memory. And so this is the sort of algorithm we actually implement. I just used Lagrangian formulation so that I could use an accelerated proximal gradient method. And I use the TFOX library, but I mean, there are of course dozens of different ways of solvers for these sorts of equations, and whichever one you prefer, you could use to solve these sorts of things. But what's nice is you can also, about the convex optimization approach, is you can also encode constraints into the program. So these linear constraints down here, if you happen to know that the function is submodular, you can encode that, and that will improve the recovery. So we tested on tracking the evolution of a graph. So on the SNAP website, there's a graph that evolves, or a few snapshots of a graph as it evolves from week to week, and then we take the measurements that I spoke of at the beginning, and you see that you need roughly 8 times the number of changes in the graph. That's the number of measurements that you need total in order to have low error in detecting what the changes are. And so also, if you happen to know that the function is submodular, this is an example. So this is only on synthetic data, but it shows that you have much lower recovery error if you happen to encode as a constraint submodularity. So we take a random function and project it onto the cone of third-order submodular functions, and then just try to reconstruct it based on measurements in 3 different ways. One, just minimizing the L1 norm. Another with an oracle who knows the signs of the coefficients. And then lastly, by not knowing the signs of the coefficients, but just minimizing L1 subject to the linear constraints and submodularity constraints. And I didn't mention, but there's actually a closed form formula for whether there's a way to write down a necessary and sufficient condition in the Fourier domain for third-order submodular functions. And so enforcing the coefficient signs reduces the error, and but enforcing submodularity reduces the error much further. This is just an example of approximating a function by a second-order function. So this was a mutual information function, and it was just an example of showing how well you can approximate this function by just second-order functions. So the conclusion is that we can apply techniques from compressed sensing and sparse recovery to learning set functions, and I think it's an interesting approach for doing set function recovery, and it's a new, potentially interesting application for sparse recovery results. But this is just the first step, because there's much more problem structure that needs to be exploited to improve performance, just in terms of both reconstruction performance and actual reducing computation time. So thanks very much, and if you have any questions.
Are there questions? Questions? Yes?
Yeah.
So there's an interesting thing. So basically, your Fourier transform is a Mobius inverse. And there's an interesting, it's not really a question or a statement, but you've got this, you can frame if you use, rather than the subset inclusion, if you use superset inclusion, you can actually compute the cliques as the superset, as the Mobius, as the same functions in superset inclusion, like graph edges.
Right.
Cliques and separators.
I mean, the Mobius transform is a little different because you can actually compute it, like you don't, because it's not a sum over exponentially many things, right?
Yeah, maybe like.
So I mean, this is really, it's really also well known as Hadamard transform, but it's applied to this really large object, this set function. So I mean, there is a fast transform. There is a fast Hadamard transform for this, but it's just instead of to the n, to the 2n, it's to the n log to the n. So that's still like very exponentially slow to implement.
Well, what I was going to say is that you probably get the same results for these sort of structural graphical model estimation, structural learning things. You can phrase that in terms of this.
Right. So the key thing is you need some sort of incoherence condition.
Yeah.
So the Fourier transform is like perfectly suited for these random matrix results where you're sampling a bounded orthonormal system. So it's exactly a special case where these results from random matrix theory apply. And so I think maybe the Mobius transform might also be useful, but I'm not sure those results would apply directly.
I was just thinking you then frame a lot of the sort of graphical model estimation in terms of your problem, which is then already your it's interesting.
Next question?
So it seems that for your thing to work, you need to be able to maybe limit to some tractably large subset. So that's your low order condition, and then you need the sparsity assumption. So what's your intuition beyond the cut functions? Like when it would be appropriate?
Well, I mean, that's sort of where the bounds come into play, because we'd really like to be able to prove something about how the Fourier spectrum decays, and what sort of conditions do you need in order to get that decay, so that you can get away with both assumptions that it is well approximated by low order and it is fairly sparse.
So my question is like more what kind of applications would correspond to these technical conditions?
Well, so any sort of set function where I think there's some sort of maybe locality where only near elements in this, adding or removing an element in a set can only influence similar elements in some space. So in other words, for the mutual information example, that was a set function over whether or not to place sensors, and those sensors are located in some physical space, right? And so, therefore, the function's there's only really higher order interaction if the elements are close to each other. The sensors are physically close to each other. Otherwise, it's essentially like a low order function. It's a modular function.
Other questions? Is this, do you impose orthogonality in your transform space?
Well, I mean, by definition, it already is orthogonal. So there's no, it'd be interesting to look at, again, non-orthogonal superpositions, or a function class where they're maybe not orthogonal, but this is they already are orthogonal, so that's what it's about.
So in some sense, I mean, given the previous results, right, from Canvas and Tau, it seems like all this new theory should be non-surprising in a way, because you're proving it in a different domain, right?
Sure, it's more just it's applying it to a domain where it hasn't been applied to before.
Right. Is there any surprising technical difficulty when you're doing this work?
No, I mean the technical results were just some of those bounds I gave you, but and there's a little bit more in the paper, but no. I mean the heavy lifting has been done by Verschinen and Rauhat in this work, so.
Is there analogous physical meaning of this Fourier coefficients that you have, like in continuous domain? These are frequency. Mm-hmm. So here, what kind of? Essentially,
it means like what the level of interaction between these elements is. So for the graph code example, it means that it's directly in the graph code example. It's directly proportional to the weight of the edge between those two nodes. So you can sort of generalize this to hypergraphs where you've got cliques, and it's the Fourier coefficients correspond to like how strongly these things interact, like when you add or remove an element.
Are there other questions?
So going back to the motivation at the beginning.
Mm-hmm.
So you say this graph is really big, so you might not want to store it, but then you want to compute sort of several graph cuts all the time. So it seems like, so what are you gaining really? You go from...
It's mainly a gain in storage. I mean, you don't need to compute that graph cut all at once. I mean, you could compute it in an online fashion if you only revealed the graph sequentially, but it's mainly just you don't want to download this entire graph. You're just interested. Well, you don't want to save the entire graph from week to week to month to month. That's the main benefit there.
Okay, so I mean, like, what sort of practically, what would be a situation where this would actually be good?
Yeah, like a social network or something where you're just not interested in storing. I mean, you're not interested in. You only have access to maybe a limited. You only have access to the graph at limited times, and you really just want to store a small set of measurements to summarize essentially everything that you know about it.
Okay. Yeah, so let's thank all the speakers.